Hello everyone, my name is Daniil Kirilenko and I am going to present a paper on learning heuristic functions from grid-based pathfinding via transformers. This is a joint work with Anton Andreychuk, Alexander Panov and Konstantin Yakovlev. Pathfinding problem naturally arises in various applications, like robotics, computer games and others, and it generally asks to find a collision-free path for an agent in the given environment. Often in AI, this problem is reduced to finding a path on a graph representing the agent's workspace. Within this approach, first the workspace is discretized to a graph, and then the graph search algorithm, like A star, is invoked. In this work, we follow this approach and use an 8-connected grid to model the environment. It is one of the most widespread ways to do so, as grids are simple yet informative and easy to construct graphs widely used in pathfinding. The standard way to find a path on a grid is to invoke a heuristic search algorithm like A star, which iteratively explores the search space. The performance of A star heavily depends on the heuristic function given as an input to the algorithm. Heuristic function estimates the distance to the goal node and is used to focus the search to the goal. One of the most common heuristic functions for 8 connected grids is the octile distance. It's a closed-loop formula that measures the distance between the grid cells. Octile distance is a consistent heuristic, which means that A star is guaranteed to find an optimal path. The major drawback of using octile distance or other similar heuristics is that they are not instance dependent, namely, they don't take obstacles into account. Thus, in the obstacle-rich environments, A star might suffer from poor performance due to extensive explorations of the search space. A common way to make the heuristic more informative and to decrease the number of the explored nodes is the so-called weighting the heuristic. It means multiplying it by a certain factor. The resultant algorithm is called weighted A star. Still, this technique is limited and in practice, the number of the explored nodes can be high. Ideally, we want to have a perfect heuristic that for every node knows the exact cost of the shortest path, circumnavigation of all of the obstacles to the goal. A star with such a heuristic will expand only the nodes lying on the shortest path from start to goal. Motivated by this, in our work we utilize the state-of-the-art machine learning techniques in order to obtain the accurate approximation of the perfect instance-dependent heuristic function that takes obstacles into account. We utilized modern neural networks, namely transformers, for this. At first, we need to train the neural network using ground truth values obtained from the expensive uninformed search from the goal node. Then we can use predictions from the trained neural network to improve the basic search algorithm. We are not the first to suggest such an idea, and there exist works that utilize neural networks for grid-based pathfinding. Here we mention the two of the most relevant ones. In the work by Takahashi and others, it was proposed to use convolutional neural networks to infer the approximate values of the perfect cost-to-go heuristic function based on the image representation of the pathfinding instance. In the most recent work by Unitani and others, the differentiable A star model was introduced, which was used to train a neural network to predict the cost of the certain moves on the grid. In our work, we use both of these approaches as the baselines to compare with. Later we will show that our method consistently demonstrates better results. We propose predicting two types of heuristic functions. The first type of heuristic is the correction factor, which is defined as the ratio of the value of the available instance-independent heuristic to the value of the perfect heuristic. In general, predicting CF values may seem similar to predicting the values of the perfect heuristic, as was proposed in previous works. However, there is a difference. First, the correction factor is bounded and lies in the 0-1 interval. Second, the correction factor encompasses more information as it is a combination of both instance-independent and instance-dependent heuristics. To get ground truth CF values, we use an uninformed search from the goal node. At the testing phase, we plug in the correction factor as an additional weight to the weighted A-star algorithm. The second type of heuristic is a path probability map. This heuristic is designed to demonstrate how likely the node is lying on the shortest path from the start to the goal. Since there are many shortest paths on the 8 connected grids, in general we need to break ties between them when constructing the ground truth ppm values. To this end, we utilized theta star and any angle search algorithm. Theta star paths are formed of the waypoints located at the corners of the obstacles and cells that lie on the straight line segments connecting the waypoints. In the resultant ppm, we assign the values of 1 for such paths. For all other cells, we computed the values that tell us how close the cost of the path through the cell n to the one of theta star is. Values that are lower than 0.95 were set to 0 in order to get narrow path tunnels. After training, ppm can be used as a secondary heuristic inside the focal search. It is a technique to lower the number of search iterations via exploiting an additional list of nodes called focal with secondary heuristic values. This allows us to get the solutions which cost is guaranteed to be bounded by the user-provided factor. Each of the proposed heuristic functions is used in a different version of a generic heuristic search algorithm depicted on the slide. Correction factor values are used as weights in the instance-independent heuristic in the weighted A-star. Path probability map is used as a secondary heuristic in the focal search. Moreover, if the suboptimality factor in the focal search is large enough, it turns into greedy best first search, where the nodes are chosen based only on their ppm values. The architecture of the model that we use to predict proposed heuristics has three main blocks: convolutional encoder, spatial transformer, and convolutional decoder. Convolutional encoder utilizes ResNet blocks and is aimed at extracting the local features of the pathfinding instance, such as corners of obstacles, narrow passages, etc. Transformer leverages the mechanism of self-attention to establish the global relations between these features. Finally, the transformed feature map of the pathfinding instances are processed by the convolutional decoder, which provides the final output. The network is quite small and includes only 1 million parameters. We train each model using direct supervision with mean squared error as a training signal. We have adapted the tiled motion planning dataset that was used in previous work for empirical evaluation. This dataset is a modification of the motion planning dataset, which consists of maps with various challenging topologies such as backtraps, gaps, etc. Each map in the TMP is composed of the 4 such maps. We further increased the size of the dataset to 64,000 maps via the augmentation by mirroring and rotating each of the 4 parts of the TMP maps. For each final map, we generated 10 problem instances. Goal location was chosen randomly, while the start one was chosen out of 1/3 of the reachable nodes that have the highest cost of the path from the goal. Thus, 640,000 instances comprised the dataset. To measure the performance of the models, we use the following metrics: expansions ratio, the ratio of the number of expansions performed by the planner to the number of A-star expansions; cost ratio, the same ratio but for the solution cost; and optimal found ratio, the ratio of instances optimally solved by the planner. Here is a list of the methods we consider in our experiments. A-star and weighted A-star are non-trainable baselines. Neural A-star with predicted cost of the moves and A-star with predicted perfect heuristic are trainable baselines. Our approaches include weighted A-star with predicted CF values and 2 versions of the focal search that utilizes predicted path probability values. Table on the slide shows the evaluated matrix for the dataset. Clearly, all the learning-based planners are able to generalize to the unseen instances, solving them near optimally while reducing the search effort. In terms of cost ratio, the best results are demonstrated by focal search with ppm, while the other hour planner weighted A star with CF values turned out to outperform the competitors in terms of number of instances solved optimally. Figure on the bottom of the slide shows several instances from the dataset with the solutions obtained by the evaluated algorithms and the nodes they expand. The techniques suggested in our work outperform the competitors. To demonstrate the importance of using the transformer block in our model, we replaced them by ResNet blocks. We trained this model similarly to the base model, and clearly the usage of transformers notably increases the performance across all of the considered metrics, as the table on the slide tells. The figure on the slide shows an example where CNN model predicts a fragmented guidance path, while the transformer constructs a continuous path tunnels. This confirms our hypothesis that transformer is crucial to capture the global patterns and interdependencies between the local features of the maps. In this example, it was able to detect that a prolonged path segment is needed to connect two waypoints located in different parts of the map. Besides the main dataset, we have also created an out-of-distribution dataset that consisted of 3 different maps taken from the Moving AI benchmark to evaluate generalization capabilities of the trained models. Each of the maps was scaled to 2 different sizes, and there were 1000 randomly generated instances per each map and size. We didn't perform any additional training for these maps. The table on the slide presents the aggregated results. As expected, the performance of all the learnable planners is worse compared to the main experiments. Still, the best results in terms of expansion ratio is achieved by one of our planners. To conclude, in this work we explored how state-of-the-art deep learning techniques may aid heuristic search planners in solving grid-based pathfinding problems. We have suggested to utilize a deep neural network composed of both convolutional and attention layers to predict several novel heuristics that can be used in combination with weighted A star and focal search. We showed empirically that the suggested planners were able to successfully outperform the competitors that include both traditional heuristic search techniques as well as the state-of-the-art learnable approaches. The avenues for future research include but not limited to planning in 3D and planning with kinodynamic constraints, etc. This is the end of my presentation. Thank you for your attention. Check the paper and the code repository for more details.